Check, check. Nope. Yes. Test. Morning, Roman.
Good morning, Professor.
Hear me okay? See the screen all right?
Yes, sir.
All right. You ready to get into this? Grab something real quick. Okay, I think we're ready to go here. I hope y'all had a good weekend. We are finishing up 6-3, hopefully finishing up 6-3 today. We spent we spent all of last class going over the first part of this section, which was just preparing us for what we're going to do now. So I hope you had some opportunity to review partial fractions a little bit. And then did you bring your calculators? Hopefully you did. If you didn't, well, you'll follow along. All right, so our goal here is to be able to find the antiderivative of rational functions. So we need to make sure we understand what a rational function is. This is a college algebra idea. You take a polynomial divided by another polynomial, and that's a rational function. So any function p of x over q of x, where q of x isn't 0, is a rational function. And those two functions have to be polynomials. All right, so here's some examples of polynomials. All right, all of those look terrible if you imagine trying to integrate each of those. And so that's what we're here for, to try and figure out what the technique is. And so in pre-cal or the end of college algebra, at some point you should have done the partial fraction decomposition. We'll review that, but here's the general strategy. Okay, so when you're looking at a rational function and you're trying to find the antiderivative, the first step is to inspect the degree. Oh, you know what? I need to open a program here. Where is it? Make sure this is open. Yeah. Okay. The first thing you want to do is inspect the degree of the numerator and denominator. And that just look at the highest power of x you see in the top and the bottom. And then that will tell you what to do, whether or not you're going to have to do long division or you can move on. So if the degree of the numerator is smaller than the degree of the denominator, we just move on to the next step. That's the good case. If that is not the case, if the degree of the numerator is greater than or equal to, okay? So if the top one is the same as the bottom one, or the top one is bigger than the bottom one, either way, we'll have to do long division first, which is the good old-fashioned division box and all that stuff, okay? So once we have done that, we either have moved on or we have done the long division. The remaining rational function that we have, see, if we do long division, we're going to have a new rational function. If we don't do long division, we're still going to have the original rational function. Either way, you look at that part and then you do your partial fraction decomposition. So partial fraction decomposition all comes down to you factor the denominator, okay? And then you look at those factors and you determine what kind of factors they are. So are they linear? Are they quadratic? All right. Are they repeated or not? And so there's a whole set of processes that you can learn in a very abstract way that I think is somewhat just kind of ugly to look at. I think sometimes it's better if you just see it worked in examples for you to understand how partial fraction decomposition works. What I did want to kind of mention here, because this is Cal 2, is this whole idea of using these subscripts on things. This happens whenever you start to generalize math. We get these subscripts on letters. So let me just motivate this with an idea, with an example. Let's just for the sake of me trying to point something out here, let's say we had a rational function that looked like this. Whoa, that's a 1. Let's say it was like x plus 1 on the bottom. We had factored the denominator, x plus 2, x plus 3, x plus 4. I'm just making this up, okay? X plus 5. And let's say it kept on doing this pattern all the way to x plus 100. Okay? Look, we're not going to integrate this. I'm trying to point something out to you. That is a rational function, isn't it? The top is a polynomial, 1, the constant 1 function is a polynomial. And then divided by, well, that's just a bunch of linear factors multiplied together, right? So that would be a polynomial also. It's already factored. So if we were going to do partial fraction decomposition on this, what we would have to do is look at each of these distinct linear factors. How many of them are there? There's 100 of them, okay? And so for each distinct linear factor, we would say that this fraction turns into some number, we don't know, so we'll call it A, over the first linear factor, plus now the second linear factor, some number we don't know, B, over the second linear factor, plus some number C over the third linear factor. And we would do that all the way till we got out to the last one, right? So if we were integrating this and we were successful in the partial fraction decomposition, do y'all understand how easy it would be to integrate each of those? Do y'all recognize that these are all just constant over linear, which we did last time? Those would all turn into natural logs, and we could do those like that. The hard part would be breaking it down from this to this, right? So if I do this, A, B, C, D, what's wrong? I'm going to run out of letters, right? Because there's 100 of these, right? And so I only have 26 letters to work with in the alphabet, and I'm already using X. So I actually have 25 letters. So I'm going to run out. So instead of doing that, what we do to generalize things in math is we stop doing that and we just do subscripts. I do A sub 1, A sub 2, A sub 3, and then I can go out as far as I ever need to go. Okay, so anytime we see these little subscripts like that, it's not to try and make math complicated. It's only because we run out of letters eventually, right? So we try and generalize it to a point where we can handle anything, right? Now, fortunately for us, we are never going to have to do something like that. We're going to stick to maybe like 4 or 5 letters. So in class, I am going to use A, B, C, D for those things on top, all right? But when you look at my notes, you'll notice I don't do that, right? In my notes, I say, hey, look, if you have a polynomial where the bottom has linear factor, and you have n of these linear factors, then you're going to do A sub 1 over the first linear factor plus A sub 2 over the second linear factor, and so on and so forth. Okay, so that's why I don't want to go through the notes. I think it's a little bit cumbersome to deal with that notation. Okay, so let's do something. Let's just start working these examples. I think that would be the best way for us to kind of get warmed up to this idea. So this first integral we're going to do, come on. What was it? X cubed? Sorry, let me just paste it here. Oh, x cubed plus x over x minus 1 dx. All right. So now we've reached the end, right? So now you have to consider everything you learned, right? Is this something basic from Cal 1? Is this power rule? Is this integration by parts? Is this a trigonometric integral, right? Or is it partial fractions? I am always going to check first to see if I can do this with like a basic U sub, or maybe even split it into two, right? I could do like x cubed over x minus 1 and then x over x minus 1. But neither one of those is going to be something that gets us there directly. So I've kind of come to the end where I'm like, well, it is a rational function, right? So I'm going to inspect the degree of the numerator and denominator. So the degree of the numerator is 3. The degree of the denominator, even though it's not written, is 1. And in this case, the degree of the numerator is bigger, right, than the denominator. So I must do long division first. Okay, so we're going to fall back on college algebra now. Long division, you always put the numerator in the division box. And in this case, the numerator is x cubed plus x, right? Now, depending on how you learned long division in college algebra, the way that I teach it is that I always leave spaces for any powers of x I don't have. So this is a cubic, right? A cubic polynomial on top, but I'm missing the squared term on x and I'm missing a constant. So in my long division box, I left a space in there for any x squared terms that might appear when I do the long division. If you don't put that space in there, you might run into some issues trying to squeeze things in, you'll confuse yourself. So that goes on the inside. On the outside, the x minus 1. I should also point out that both of these polynomials are written in descending order. So highest power of x down. So from the left to right, highest power of x down. All right, how do you do this? If you had to explain this to somebody, what you're going to do now, how would you explain this next step? Okay, yeah, so you're looking at this x cubed and you're looking at the x, not the minus 1, right? You're just saying to yourself, what you said, take x cubed and divide it by x, right? Which is the same as saying, what do you multiply x by to get x cubed, right? Same, you get the same result. So however you want to look at it.
I would just put it like x cubed on the top, x
Over,
bottom, and
cancel and you get x squared. Okay, so I'm going to put an x squared up top. Now, where you put it, again, doesn't matter, but some people were taught just line it up above the x squared since you're putting x squared. It's up to you. It's the answer. So x squared up here. Now, once you get x squared, what do you do with that? You multiply it through to both of these terms, right? So I multiply x squared times x, and where do I put that? Because x squared times x is x cubed, right? I put it underneath this x cubed. And then don't forget, you have to do x squared times negative 1, which is negative x squared. I got you, right? Negative x squared. Then we come through and subtract this row, right? And when you subtract that row, that's the same as changing the signs. So this becomes minus, this becomes plus. Oh, see how I put the x squared underneath that? See, if you didn't have that gap in there, where would you put it, right? You can't put it under the x because those aren't like terms. So, okay, the x cubes cancel. That's the whole point of this. It should. And then now we add down 0x squared plus x squared should give us just x squared. And then I add down x plus nothing. There's nothing under here, so plus x. And then I don't need to put the plus 0, but there is a plus 0 out here. Okay, that's our first step. And then our next step is to do it again, right? We do it again, but now we look at the x squared. instead of that x cubed. So you can either do it the way Cruz is doing it, right? Take x squared, divide by x, or you can do it the way I'm doing it, where I say, oh, what do I multiply x by to get x squared? X, right? So plus x. And then we distribute that through again. X times x gives me x squared. Put it underneath the x squared. X times -1 gives me negative x. Are those x's going to cancel? No, because I need to subtract, right? Don't forget, you got to subtract. So subtract, which changes the signs. And now you add down. So when we add down here, the x squareds go away and we get 2x. And then we just keep playing this game, right? At some point we stop though. We stop when, well, let's see, when we can't do this anymore, right? When we can't multiply by something nice. Here we can go again, can't we? We could multiply to get 2x, we can multiply x by 2. So I'm gonna do 2 here. All right, 2, here we go. 2 times x, that gave me a 2x underneath, and then 2 times -1 gives me -2. I come through, I change the signs. This is minus, this is plus. They cancel, and I get a 2. Right, here, now we're finally here. Because you can't turn x into 2 with anything other than a fraction. You could do it, right? Couldn't you multiply this by 2 over x? What's x times 2 over x? 2, right? So you could, but you stop long division when you can't multiply by something. Well, if it, how do I say it? It has to be a term of a polynomial. It can't be a fraction. Okay, so at this point I stop. And this is my remainder, right? So I take my remainder, which is what? 2, and I put it over the divisor, which is x minus 1. So at the very end, it's always the remainder, which is the 2, divided by the divisor, which is x minus 1. And that's it. We are ready to, all we've done at this point is taken this expression and rewritten it in an equivalent form. It's as simple as this. It's like me taking the number 15 over 5 and rewriting it as the number 3, right? I'm taking a fraction and rewriting it in different form. It's a very ugly looking thing, all right? Okay, so here we go. Here's our new integral. Integral x squared plus x plus 2 plus 2 over x minus 1, all of that dx. And now we look at each of those pieces and we ask ourselves, can we find the antiderivative, right? And all of these are doable, right? These are all, we all wish that our next test would just be a bunch of those, right? So this would become 1/3 x cubed plus 1/2 x squared plus 2x plus, what about that last one? 2 times the natural log of the absolute value of x minus 1 plus c. So please keep in mind that from here to here was what we did on Thursday. No, sorry, Wednesday, right? We said if we have a constant over linear, we can do that easily with natural logs. And we went around the room, we did a bunch of them, okay? That's it, we're done, okay? This required no partial fractions. All this was long division, right? There were no partial fraction decomposition at all in this problem. Okay. That's the first problem. So any questions on that? How do y'all feel with the long division? I know it's probably been a while, but is it, I don't know, it's just something students always have, like they just don't like it. Easy. Do you think there's a lot of places to make mistakes?
No.
Forget the process? Okay. Do y'all understand the process? Do I need to go through the process? We're gonna do a couple more that are gonna require it, so. Yeah. Yeah, synthetic division, right? Yeah, so what's the deal? Why didn't I use synthetic division here? Because synthetic would have worked out very fast. Why do you think I didn't do synthetic? You could have. There's a limitation to synthetic. Do y'all remember what the limitation is? What do you mean power? So it has something, you're right, it has something to do with power. Synthetic division only works if your divisor, what the hell? If your divisor is linear. If that divisor is something other than linear, like let's say it was quadratic, synthetic's out the door. Okay, can't use it. Long division works both in all cases. So long division is more powerful. And so that's the only thing I show in Cal 2. In college algebra, you use synthetic because you're factoring polynomials, quadratics, and then you're using this thing called the rational zero test to try and break things down. But here, we're just going to crank out the long division because we're in Cal 2, so it doesn't scare us anymore. Right? Okay, let's look at this one. I love synthetic, but you got to have a lot of things go your way to use it, at least once you get past college algebra. Okay, here we go. Okay, you know what? One thing I would do here, if this were me doing the problem, which it is, is I would recognize something right off the bat. The bottom is cubic, right? And the numerator is quadratic. Maybe if I'm lucky, I could let u be the denominator. And then maybe the top is the derivative of the bottom. Maybe. Let me check it real quick. I don't think it's going to work. Do you understand what I'm saying? Because it's cubic on the bottom, if I grab the whole thing, maybe if I take its derivative, it's 6x squared plus 6x minus 2 dx. Is that what the numerator is? No, right? I can't factor out anything. I could, yeah, there's no way I can make. Now, do you remember last class? I showed you a way where I said, this is the way I do it. This is the way other, remember that? That technique I showed you is only valid if your denominator is quadratic and your numerator is linear. Once you have this, where the denominator is cubic and the top is quadratic, there's nothing that I can do to massage the top to make it look like the bottom. It's just not going to happen. So I didn't get lucky. I remember one semester I put a problem like this on the test where it did work and nobody got it through the U sub. Everyone did partial fractions, which you can get the answer still. Okay, so the moral of the story is always be looking for the path of least resistance here. Don't just automatically go where you know what I'm saying? I don't think I'll do that to you, but it would be a gimme problem, wouldn't it? Wouldn't that be a gimme problem if I just made it, like the bottom's U, the top is DU, you're done? But I'd be afraid you'd miss it and spend too much time on it. Okay, here we go. So it doesn't work, so I need to do something. Well, nothing else, integration by parts, nothing else looks fun. It is a rational function. I look at the numerator, the degree, it's 2. The denominator, it's 3. Do I need long division? No, right? Okay, so I don't need long division. That means I need partial fractions now. And to do partial fractions, I have to be able to factor the denominator. So let me go try and factor the denominator. I'm gonna do that over here. 2x cubed plus 3x squared minus 2x. The only thing that I can do initially is a GCF, greatest common factor. I can pull an x out. Right? And then 2x squared plus 3x minus 2, I believe that does factor. What do we have? 2x minus 1 plus 2. Is that right? That doesn't look right. That's not right, is it? No, other way around. Plus 2 here. Minus 1. Does that work? No, yeah, sorry. Hold on. X. Okay, so that'll give me my 2x squared. That's 3. That's 4, and then take away 1. It's 3. This good? Think so. Well, let's run through FOIL. 2x squared. Yay. Okay. 2x times 2 is 4x. And the middle term is minus x. So 4x minus x is 3x. And then -1 times 2 is -2. Okay, so that is the correct factoring of that, right? I have to assume you can do that. We're in Cal 2. So maybe it takes you a little more time on the side, but the assumption is that you could factor a quadratic. Okay, we good? So now I'm going to rewrite the integral. I'm going to scroll down here a little bit. I've got integral, let's see, x squared plus 2x plus 1 over minus 1. Thank you. Thank you for catching that. That would have been a disaster later. And then we have on the bottom x, and then 2x minus 1, and then x plus 2 dx. Okay, so that is the first step for the partial fractions, right? Factor the denominator. Now you look at the factors in the denominator and you identify what they are. So how many factors do we have? 3. So we have 3 factors. Each one of them is linear, right? They're all linear. And they're distinct. Distinct means they're different from one another, right? So we have here 3 distinct linear factors. And so that means as I go to start doing my partial fraction decomposition over here, so this is a separate kind of step. I'm back in pre-cal or college algebra or whatever, and I'm doing partial fraction decomposition over here. What I know is that this should break down to be some number over each of these 3 distinct linear factors. So some number, I don't know, a, over the first distinct linear factor x, plus b over the second distinct linear factor, plus c over the third distinct linear factor. Yeah? And now our goal at this point is to do what? What is our goal? What do we need in order to be able to finish this off? Find A, B, and C, right? Goal, find A, B, and C. See, because if we knew what A, B, and C are, right? If we knew what these were, these are numbers. If we knew what they were, then the original integral becomes this, the integral of these 3 things. And each of those is constant over linear, constant over linear, constant over linear. That's what we did last class. We'll be happy, won't we? Does anyone remember in pre-cal or in college algebra when you learned partial fractions? Did your professor tell you it's because in Cal 2 you'll need it to? No, you don't remember that? Yeah, I always tell my college algebra by pre-cal students, this always comes up in, if you take calculus later, it'll come up. And I also tell them in my videos that I'm in Cal 2, they won't show you how to do it. I'm lying to them because we're kind of reviewing here a little bit. We're just not going to get deep into it. Okay, so I need to go do this now, right? So here we go. So what is the next step for this? Yep, you're going to clear the fractions. So you're going to multiply everything, both sides of the equation by that. Okay, so we're going to multiply both sides by that. So let's do that. The left side by this. And then everything on the right will be hit with this also. And on the left side, things are great. Everything just goes away. On the right side, we must distribute this through here, here, and here. So when I do my first multiplication, this big chunk of stuff times that a over x, this x on the bottom will kill off this x, won't it? So I'll be left with the a, and I'll be left with the 2x minus 1, and I'll be left with the x plus 2. When I do the second multiplication through to the b over 2x minus 1, the 2x minus 1 factor will cancel. So I'll still have the b there. I'll still have an x. I'll still have an x plus 2. And then on the last one, the x plus 2 factors will cancel. So I'll have the c, the x, and the 2x minus 1. Questions? And then here's where we have the opportunity to do one of two things. The short method or the long method, all right? So the short method will work when you have distinct linear factors. If that's all you have are distinct linear factors, the short way will always work. If you don't, then you might need the long way. But we are going to use our calculators also today. So we have like the ultimate, save us thing here to do it. Now, let's do the short way here. I'm going to show you the short method first. The short method works like this. What you're going to do is try and get A, B, and C one at a time. So let's try and find A. So to find A, to figure out what A is, I'm going to try and pick a value of X that will kill off everything here and everything here simultaneously without killing this off. Can someone see it? 0. If I let that X be 0 and I let that X be 0, it'll kill everything off here, kill everything off here. But see, since this doesn't have an X term, it won't kill that off. So I'm now going to do that. I'm going to let X be 0. And I'm going to rewrite the equation. That means replace everything in this equation, all the X's with zeros. So what's the left side of the equation become? -1 equals A, 0 minus 1, 0 plus 2, and then everything else is gone. So I just replaced that X with 0, replace that X with 0, and then everything else got killed off. So this is really -1 times 2, isn't it, right here? So this becomes -1 equals A times -2. I'll divide both sides by -2, and I will get 1/2 for A. I'm a third of the way there, right? I have A. Questions? Got to get B now. So to find B, I'm going to let X be something else. So if I want this B to stay here, this B term, right? Everything here. I want to kill the A and the C off. What I look for is what factor the A and the C have in common, which is the 2x minus 1. See that? They both have 2x minus 1, but this one doesn't. So what would you have to plug in for X to make the 2x minus 1 become a 0? 1/2, right? Positive 1/2. So I'm going to let X be a 1/2. You understand that? Okay, we got to do that in the whole equation. So that's going to suck. The left side, I've got to do, X squared. So what's 1/2 squared? 1/4. Okay, so this is 1/4 plus 2 times 1/2. That's going to just be 1. Then minus 1 equals. So that's the left side. Now the right side, we know this is all dead. We know the C part's dead. So it's just this B part. B times 1/2, then 1/2 plus 2. I think some nice things happen on the left side. Y'all see that? half of 2 is 1, and that kills off right there. So we just have a fourth on the left side equals, okay, let me see here. We have 2 plus a half, 5 halves. 5 halves times a half. Is that 5 fourths? Okay. So 5 over 4b. And however you want to do this, you could divide both sides by 5 fourths, or you can multiply both sides by 4 fifths. Either way, you should get b as a fifth. Geez, come on. Questions on that? B is 1/5. One more to go. Okay, let's find C. We haven't fun yet? Let's find C. Okay, to find C, yeah, this is a short way. To find C, let me grab this and bring it down here. What are we going to have to let x be to find C? -2. So we're going to let x be -2. All right, if we do that, the left side becomes 4 minus 4 minus 1. So I'm squaring -2, gives me 4, and I'm doing 2 times -2, which gives me -4, and then -1. Everything dies except the last piece, C times -2 times -4 minus 1. I think I got that right. So -2 here, -2 right there gives me -4 minus 1. So, okay, I think this is good. 4's cancel. -1 here. What is this? All these numbers together here. 10. So 10C. So C is finally -1/10. There we go. All right, I have what A, B, and C are now. All right. So back to the beginning here. Where were we? All right. I'm going to copy this right here. Copy that again. I'm going to need your help here in a moment. So here's what we've got. We did the partial fraction decomposition on this. And so we know A was what? A half. So I'm going to just put that above the X. And then what was B? The -1/5. That goes above there. And then the C is -1/10. Right? Was it a positive? Okay. I thought I said negative and someone agreed with me. So positive a half, positive a fifth, -1/10. We good? Okay, now let's go back to the original thing, which was to find the antiderivative of this, right? We want to do the integral of this, which means we really want the integral of this. Now that 1/2 and the 1/5 and -1/10, those really don't matter. Look, I can rewrite this as 1/2 integral 1 over x dx plus 1/5 integral 1 over 2x minus 1 dx minus 1/10 integral 1 over x plus 2 dx. See, I'm splitting it into 3 integrals. The constants that we found, A, B, and C up top, we just pull them all out in front of the integrals. And now each one of these 3 integrals is a constant over linear, right? Which should turn into natural logs. We have to be careful though. The first one is just 1/2 natural log absolute value of x. Next one is 1/5. Okay, here's the part that's tricky. What is the antiderivative of this? It'll be 1/10. So you're going to get a 1/2 to come out of this, right? Because of the A, the number in front of the X. So you'll actually have a 1/2 next to the 1/5, which Cruz said will become a 1/10. Natural log of 2x minus 1. And then minus 1/10. Do we have anything pop out on this one? Do we have to scale? No. So just natural log of x plus 2 plus c. So yeah, maybe the last step is just to put those two together, 1/10. Question or comment? What's going on?
If you were to take out the 1/2, wouldn't that affect the negative 1?
The 1/2.
That right there where the mouse is at.
If I were to take out the 1/2.
Oh, wait, never mind. I thought you were taking it out. Sorry.
No, what I'm doing is, remember when we do constant over linear, we always have to pay attention to the linear. If there's a number in front, we have to scale it out. Because if we took the derivative of this, right? It'd be 1 over that times 2, because you have to do chain rule, derivative inside. And so to kill off the 2 that would pop out in chain rule, we put a 1/2 out here.
Yeah.
You sure?
Yeah, I thought you were taking the 1/2 out. I didn't
Like
see
the
that
1
taking
over
it.
2.
Yeah.
Oh, you were thinking I was factoring a 2 out, which would have changed that to a 1/2. You could do that too. It'd work the same way. But this would be a 1/2 now. And then this would change to x minus 1/2.
Yeah, that's not bad.
Yeah, no, it's fine. Okay, what do you think? We're done. It only took however long that took. Okay, so that was a short method, right? Let's go back up and do it the long way, but we're going to use our calculator, so it may not be as long. Okay, let me see here. I'm going to go back up to where we had this, no, where we had cleaned it up. Hold on, where did we clean it up? Right here. This line right here is where we did the short method, right? Now, here's the thing that's great. Again, the short method does not always work, okay? Because sometimes, you know how in the short method we were trying to like figure out what A is by killing off B and C, or figure out what B is by killing off A and C? Sometimes you cannot kill off everything except one. It's just not possible. Now, if they're all distinct linear, yes, you can, but if you have repeated linear or irreducible quadratics, you cannot. So the long method is more powerful, and that's the one I want everyone here to be comfortable with. So here we go. Instead of trying to figure out what A is by killing off B and C stuff, I'm going to expand this whole right side out, like algebraically multiply it all out. So I'm going to start with this right here. I'm going to FOIL that out. Now I'm going to do it in my head, but I'm going to trust that you could do it on paper or whatever. You should get A, and then everything in there should turn into 2x squared. Let me not mess this up. Plus 3x minus 2, right? That's that. I don't like brackets. I'm going to put parentheses instead. That was just so you wouldn't forget that the A has to come through still. And then on the next one, because I only have a bx out front, I can just distribute that. I don't have to FOIL. So that should become bx squared plus 2bx. Same with the last one. Distribute plus 2cx squared minus cx. Take your time on this. You mess one little thing up, it's over. All right, like it's over at that point. Of course, I wouldn't take off full points. Like if you were doing this whole problem and messed this part up, got the wrong answers on your calculator, it wouldn't be like 0. You know, you're doing partial fractions, you're doing everything right, but you mess some little thing. You can't get a perfect score on it, but it won't be the end of the world. Okay, so now last thing is just to pass that A through. Well, not last thing, that'll be the last thing with the expansion. So 2ax squared plus 3ax minus 2a. I hope y'all are paying attention to make sure I'm not making any mistakes. I'm on like 4 hours of sleep right now. So this is a very different method, right? I mean, we're not trying to like isolate and get A by itself. We're just expanding it all out. And now we collect like terms. So everything that has x squared, I'm going to group together. I'm just rearranging. That's all I'm going to do now is rearrange. 2ax squared plus bx squared plus 2cx squared. So I put all my x squareds together. Anything that has x, I'm going to put those together. So I get plus 3ax plus 2bx minus cx. And then anything that doesn't have x by itself. One more step, and then we'll be able to do the cool stuff. So now we're going to look at everything that was in blue there on the right-hand side of the equal sign. They all have an x squared, right? So we're going to factor an x squared out of just these three. Normally, when we factor, we pull things out front, right? I'm going to do it opposite. I'm going to pull it out to the back, and you'll see why. If y'all reviewed, y'all know what I'm doing here, but I'm still going to kind of treat it like you didn't review. Okay, so here, pull the x squared off the back side, and then same thing, I'm going to pull an x out of all the red ones and pull it off the back, plus 3a plus 2b minus c, and then pull the x out. And then the last one is minus 2a. All right, we have reached a critical juncture here. And that is, we are going to use the fact that this equal sign means that the left and right-hand sides have to stay balanced, meaning they have to be equal to one another, right? So if I look at the left-hand side, I have a coefficient of a 1 in front of the x squared, right? And on the right-hand side, I have all of this stuff in front of the x squared. So in order to maintain the balance, all of this together must match that number 1. So that's the first equation I can write down. I can write down that 2a plus 2b plus 2c must equal 1. Then I look at the number in front of the x, which is a positive 2. Make sure you're paying attention to the numbers here. Positive 2, right? That must match what's in front of the x over here. That gives me a second equation. 3a plus 2b minus c must equal 2. And then we have a final piece of information, that this minus 1 by itself that does not have a x in it, right? Just the constant by itself must match whatever doesn't have an x here. So that means that negative 2a has to be equal to what? Negative 1. And now what we have is a system of equations. 3 equations, 3 unknowns. Now I realize that right now you could solve for a easily, right? If you solve for a, then you should be able to go back up and get the other. And you could use elimination, which is a method you're taught in college algebra, but we are going to use this instead, okay? So who does not have, you just had your phone, right? That was all you had? Okay. Everyone else has a TI? You don't have, or do you have access to it? You do? What's your major? Yeah. Yeah, that's what we were talking about. I think it's time, if you're engineering, like it's time to have a graphic. I wouldn't go crazy. TI 84, like that one right there is a really good one. 84 plus, okay. But it's kind of the archaic system. These newer ones have nice colored graphing, and you know, that's all. It's all great, but if you don't know how to use it, it's just decoration on your desk, right? So I use the TI 89, but y'all aren't allowed to use that. But so look, what we're going to do is we're going to turn this system of equations into a matrix. Now, if you've had no like background with matrices, don't worry about it, okay? That's not what this is about. I'm just telling you what we're about to do. Turn it into a matrix, and then we're gonna do some operation that reduces that matrix down and basically gives you the answers. Okay, take linear algebra, which of course you take after this, and you learn way more about that, okay? I realize that some of you know how to solve systems of equations on your calculators already. Who knows already how to do it? Does anyone how to like enter a matrix? And okay, so if you're happy with that, stick with it, okay? What I'm about to show you is something that will work on all of the TI calculators. So as these calculators have evolved over time, the user interface has changed and how you enter things has changed. But at the base level, they all have a built-in function that does the actual solving of the system. So what I'm going to do, even though it looks weird, I know it will work for all of you. That's why I'm showing you this method. So if you're happy with your own method, stick with it. All right, so in your in Canvas under files, there is a file called RREF something, I think, or I don't know. I went ahead and got it prepared for today. This is in your, it's called RREF instructions. It's with your formulas in Canvas under files. I don't care if you print this out, you can have this during a test if you forget. So this is just a real quick showing you how to solve a system of equations. So let's do this one right here. Okay, we're going to actually do this one. So let's say we want to, and then we'll get back to the one we're working on. So time out real quick. Okay, we want to solve this system of equations. 3x plus y plus z equals 4. 2x minus 4y minus 2z equals 2. X minus y minus z equals 0. First thing we do is turn this into what's called an augmented matrix, which is basically just all the coefficients. See the coefficients on x, y, z? Okay, 3, 1, 1, 4. Now it's important that you start like have all the x's lined up, y's, z's equal number. Then you do this, right? So we'll have 3, 1, 1, 4. The next one is 2, negative 4, negative 2, 2. Boom. And then the last one is 1, negative 1, negative 1, 0. There we go. We have this matrix. Now, remember what this means. I mean, when you see a matrix like this, all it means is you have 3 times some variable, in this case, x, plus 1 times some variable, in this case, y, plus 1 times some variable, in this case, z, equals 4. That's what that line means, right? Just remember that, okay? Because what we're going to do is we're going to type that into our calculator, okay? We're going to hit enter, and it's going to spit back what's called the reduced row echelon form of the matrix. That's what RREF stands for, reduced row echelon form. That's a linear algebra thing. If you, like I said, if you take linear algebra, you'll hear more about that. So it'll spit out this final matrix right here. And I'm telling you that the last numbers are your answers. But let's see why they're the answers. What does this first row mean? 1 times the variable, right? In this case, x, 1 times x, plus how many y's? Plus how many z's? Equals 1. That means x is 1, doesn't it? And doesn't this row mean y is negative 1? And this one means z is 2, right? So the process of starting with the matrix that looks like this and turning it into this is called the reduced row echelon form. And notice that all reduced row echelon forms, what they have in common is 1s along the diagonal and 0s everywhere else. So if you can start with the matrix and get 1s along the diagonal, 0s above and below those 1s, you have done reduced row echelon form. And then the right column represents your answers. Okay, so you ready? Let's do this one. So how do you type this into your calculator, right? How do you make your calculator know you're talking about this and spit this out? Okay, here's how we do it. Everybody has to locate the RREF function on their calculator. Now this is in different menus depending on your calculator. For me, I have a math menu. Let me see. For me, I have a math menu, and there's also a matrix menu. Actually, forgotten how to get to it on here. Okay, so when you go second matrix, on mine there's math. So I go to a math menu, and then there's a matrix menu. Let me see. I want to kind of go around. Go to your matrix menu. Okay, go to edit or math. Sorry, math. There we go. Right there. Just Just hang tight. You find yours, you get something that says RREF there? No, go down further. Found it? Okay, wait. Find RREF yet? Let me see. Okay, turn on, go to, yeah, just go down to R, make sure it's RREF. Just stay right there. Stay, sorry, I didn't mean it like that. Stay, don't move. Did you get it? RREF, RREF? You got RREF yet? No, are y'all using the same kind? Can you show him? Do you mind showing him? Do you find it? Yeah, go there. Yeah, number 5. Boy, it looks a little different on that one. Oh, because you're using the CAS one. The computer algebra system one.
Does it matter or?
Just use it. Okay, just stay right there. Stay. Did you all get it? RREF? Yes? Okay, so yes? You already got it. Okay. So once you have that, okay, remember how you got to it. Go ahead and hit enter and you should be at a screen where it's actually RREF with a parenthesis. And it's like blinking, waiting for you, right? You're now going to enter that matrix into the computer. So this is calling up a function, right? And it's going to do this to a matrix. You have to let the computer know it's a matrix. So keep in mind, this is the matrix up here. What you're going to do is you're going to do a bracket, not a parenthesis, not a brace, a bracket. That first bracket, it should be above the, where's the bracket? Mine's above the comma. You put in a bracket, that lets the computer know that you are about to start entering a matrix. Then you do another bracket, and that tells your computer, here comes the first row. And then you list out the numbers of the first row, 3, 1, 1, 4, with commas between them. And then you close that off, and that ends your first row. No comma, new bracket. Okay, notice there's not a comma here, right? New bracket, type in the second row, close off the bracket. Bracket again, last row, close bracket. Double bracket on the end. And then close parenthesis to close the function off and then hit enter. Who has questions? When you're done, you should see something like this. You got it? 1, -1, 2. So if you get that answer, go solve the system that we stopped in that we were working on. Anyone have questions or need help? Were you able to get it, sir? You're good? Okay. Y'all are good here? Yeah, make sure you use the negative key, not the minus key, because that'll mess things up too. Y'all good here? Did you figure it out? Yes? Okay. So you think you'll get something? Okay, okay.
This right here where there's no number.
0, 0. Yep. Yep. Yeah. If you don't have anything there, just put zeros. I'm going to take this down. I'm going to go back to the problem we were working on. I'm going to go ahead and write down what the matrix should look like. And I'm actually going to write out exactly the way it should be typed in. So 2, 1, 2, 1. 3, 2, -1, 2, -2, 0, 0, -1. That's the matrix. And now in the calculator, it should be R, R, E, F. Well, I'm gonna have to squeeze that in there. Let me move this down here. Parenthesis, bracket, 2 comma 1 comma 2 comma 1, close, open. 3 comma 2 comma negative 1 comma 2, close, open. Negative 2 comma 0 comma 0 comma negative 1, close it, close it, close it. Did I? Oh, I forgot double bracket at the beginning. Yeah, I did. Thank you. Double bracket. The thing that's cool about knowing the actual like proper typesetting to this is that you have basically the ability to solve a system of equations of any size. Like you could go, start the matrix, you could have 30 variables in there. So you could have like 30 numbers with 30, brackets. There's no real restriction, which is really cool. I don't know if the systems, how you can put in a matrix and can you set the dimensions on it? It will let you do n by n. Okay, good. Back in the day, they used to limit it to like 3 by 3 or 4 by 4 or something like that. You can do anything. Yeah. Yeah. Okay. So again, I mean, this is just so that everyone has the same function, is familiar with it. If you have a fancier way of doing it, it's great. Any questions? What did your answers look like for this problem? Decimals, right? They're decimals. So depending on your calculator, there might be a button to go from decimal to fraction. There's a way to go from decimal to fraction. But did you get the right answers? Were they right? Was it like what, 0.5, 0.5, and then 0.2, and then negative 0.1? Did you get those answers? So you would have to convert those back into fractions, which I hope you could do. What's that? Out of 10, right? 5 tenths, 2 tenths, 1 tenth. So, okay, what do you think? Yeah? Okay. So I would prefer you use that only because, going into whatever field you're getting into, like when it comes to solving systems of equations, it's just more efficient. Like at some point you have to let the calculator do some of the tedious stuff. Okay. All right. You ready? We got to move on. Same section. We just got to move on to another problem. Okay, so I made one up before class because I wanted to do something not on my notes, just in case. Okay, so let me see here. Let's do the integral 2x cubed plus 5x squared plus 11x plus 3 over x cubed plus 2x squared plus x dx. Hey, Roman and Javier, are y'all still around?
Yes, sir.
Okay, were you able to do that on your calculator? Okay.
Yeah, I was able to get everything done.
Okay, good. Okay. So first step. The degrees are equal, which means long division. Why don't I let you? I'm going to give you 6 minutes to see if you can do that long division in 6 minutes. I'm going to start working it, but I'll just let you work while I work here. You have 3 minutes. That didn't take long. It was just one division, right? Yeah, it's just one division, so. Y'all get that? Okay, so the original integral then turns into 2 plus x squared plus 9x plus 3 over x cubed plus 2x squared plus x dx. And now that I have a plus between these, I can do these individually. So the first one's easy, right? The antiderivative of 2 is just 2x. So I get 2x plus, now this integral, I'm gonna need to do some work, right? And on the bottom, because I know I'm gonna need partial fractions, let's go ahead and try and factor the denominator out. So I can pull a GCF, right? They all have x's in them. And now that I have that, that factors, doesn't it? X squared plus 2x plus 1. What does it become? X plus 1 times x plus 1, right? So when we look at this, the x plus 1 times x plus 1, these are the same factors. So we actually have, for the first time, a repeated linear factor. So the way we normally write this is we write 2x plus integral x squared plus 9x plus 3 over x, and then we write x plus 1 squared. But I just wanted to point out to you, the reason why I'm doing that, of course, is because it's the same, right? So if we look at this, what we have is we have the x on the bottom. That is a distinct linear factor. It is unique. But then the x plus 1 is a repeated linear factor. So the question becomes, how do we handle repeated linear factors? And that, again, is a partial fraction thing. So I come over here. I'm just going to work with the part of it that's the rational function, this piece. So the way we handle this is for the x, I put an a over x, just like we had before. We'll put some letter over x, like this. And then how do we handle the repeated one? BX, well, it actually does turn out to be that, but the way it's normally taught is that you put a letter over the linear factor, and then plus another letter over the linear factor squared. So b over the linear factor, then c over the linear factor squared. What if it had been cubed? I would have had 3 of these. It would have been b over x plus 1, c over x plus 1 squared, d over x plus 1 cubed. If this was to the 4th power, it'd be b over x plus 1, c over x plus 1 squared, d over x plus 1 cubed, e over x plus 1 to the 4th. So as many as you need, just number over, or letter over it squared, letter over it cubed until you get to that highest power. All right, this is the part we're going to need to do our partial fractions, or to finish things off. So why don't we take this to the next page and go handle that. Questions? Clear the fractions? Is that a question? Okay, what you got?
The 2x, where did you get the 2x
What 2x?
for outside the interval?
Oh, because remember when we did long division, we had a 2 plus this,
Okay,
and then here's the 2 plus that, and then here I did the antiderivative of this one, but I couldn't do the antiderivative of this one yet. So the antiderivative of 2 is 2x. Let's not forget that, okay, because that is part of our answer. By the time we finish this, we might forget about this, but it's here, yeah. Okay, so here we go. Clear the fractions, right? So we multiply both sides by the denominator on the left. They cancel on the left. We get x squared plus 9x plus 3 equals. Now, when I distribute it through the first one, the x's canceled, don't they? So we just get an a and then x plus 1 squared. When I multiply it through the second part here, one of the x plus 1's cancels, only one of them. We still have a b there, we still have an x there, and we still have an x plus 1. And then we distribute to the last one. The x plus 1 squareds cancel, and we're still left with a c and an x. And this is the point where you have to decide short way or calculator way. And here, short way won't work. I mean, it might work, but it'll be a little tedious. And the reason it won't work is because if you're trying to get B, right? Let's say we're trying to get B. You can't kill off A and C at the same time. Like if you're trying to get B, you'd have to kill this off, right? So you let X be 0, but that'll kill off B. So there's no way to easily get B. Now you can get A and C and still do it, but hey, we're using our calculators now, right? So let's just go that way. So I'm going to expand out the right side. This is A times x squared plus 2x plus 1 plus bx squared plus bx plus cx is x squared plus 9x plus 3. So all I did here was expanded out x plus 1, right? X plus 1 squared is this. I distributed the bx through here, and then I got my cx on the outside. I'll pass the a through. Am I going too fast or are we good? Collect like terms. I'm going to collect like terms and factor out at the same time, just to save myself a little bit of time. This and this are the only x squared terms I have. So I would have ax squared plus bx squared. And I factor the x squared out, which leaves me with a plus b x squared plus, and then the only things that have x in them are here. Well, there's 3 things with x. So I'd have 2ax plus bx plus cx. So I'm going to put 2a plus b plus c with an x factored out of those. And then the only thing I have by itself is just an A. Now we match the coefficients, right? A 1 in front of the x squared has to match the a plus b. So a plus b is 1. The second equation tells me that 9 must match this. So a plus, oh, sorry, 2a plus bx plus c must be 9. And then the last equation is, oh, well, I know what a is, don't I? A is 3. So I don't know, maybe you go to your calculator now, but man, I know what a is. If I know a, I can get b here. And then I know a and b and I can get c. But let's just do the calculator because we're practicing. So this matrix looks like 1, 1, 0, 1, 2, 1, 1, 9, and 1, 0, 0, 3. Has anyone done it yet? Three, -2, and 5 is what you're getting. So through the RREF, we're getting 1, 0, 0, 3, 0, 1, 0, -2, 0, 0, 1, 5. No? So our answer should be 3, -2, and 5. I'm going to go back over here to this. So now my answer should be equal to 2x. See, I'm not going to forget that 2x plus the integral. And I'm going to basically be rewriting this up here with a being, say it again, 3 over x plus b was what? -2 over x plus 1. And then 5 over x plus 1 squared dx. Understand? 3, -2, 5 were our answers for A, B, and C. Can we integrate these easily? This is going to be a natural log. This is a natural log. This is not a natural log because of the squared, right? But we've done this. We did this last class. We have a constant over repeated linear factor. We did this. So I'm not going to go through all the work for this. It's not that there's a lot of work to do, but we've done it. So this should be 3 natural log of the absolute value of x minus 2 natural log of x plus 1. I just pulled the 3 out front, the -2 out front. And then this one should be -5 times x plus 1 to the -1 plus c. So if you're having trouble getting this step, this last one, just go back and look at last class, how we did that. There it is. That's the antiderivative. Questions? I want us to take a look at 2 different problems here. almost the same problems. One subtle difference between the two. You see it? Right there, right? That little subtle difference changes everything in how you go about these problems. So on the first one, well, you can factor the bottom, can't you? You could factor that bottom. And if you factor the bottom, it becomes x plus 4 over x minus 6 times x plus 3, right? And then couldn't you do partial fractions with this? Right? We would say, oh, okay, partial fractions. Okay, I want x plus 4 over x minus 6 times x plus 3 to turn into a over x minus 6 plus b over x plus 3. And then all I have to do is figure out what a and b are, right? Understand? Dot, dot, dot. We're not going to do that. That's how you would approach that problem. How is that different than this one? Well, you can't factor the bottom, all right? You cannot factor the bottom. So how do we do that? Can we do it? Let me take you back to last class. What were the things we can handle? Can we handle a linear over an irreducible quadratic, not factorable quadratic? Yes, we can. That was where I showed you the way I like to do it and the way that, you know, you might see a tutor do it. Okay? Understand? Yes? Okay, so you're taking a test. Those are two distinct roads there that you can go down. You gotta make sure you're going down the right one. So if it factors on the bottom, do your partial fractions. If it doesn't, and it's linear over irreducible quadratic, do this method. Now, the reason I showed you that is because now I want to show you another example. Okay, watch. Let's do this one. Okay, look at this one. All right, so let's just say, imagine we gotten to the point where like, okay, partial fractions. Let's try and factor the denominator. Oh, we don't have to do long division, right? I should have mentioned that. We don't have to do long division because the degree of the numerator is smaller than the denominator. So the bottom factors, I can pull an x out and I'm left with x squared plus 4, right? Dx, like that. So the method here, we look at this. This is a linear factor, right? Linear. This is what? Quadratic, but does it factor? X squared plus 4 does not factor, right? X squared minus 4 would, wouldn't it? And then I would have 3 distinct linear factors. So I could factor it all out, right? But it's plus, so it can't be reduced. So this is an irreducible quadratic, isn't it? It's an irreducible quadratic. So how does partial fractions work for this? We take the original expression, like this. And let me just pause for a second to remind you. If you have distinct linear factors, you do a over each one, right? If you have a repeated linear factor, which is the previous example, you would have to do like we did in the previous one, where we did like b over it, b over x plus 1, c over x plus 1 squared. Here, first time ever, we've had an irreducible quadratic down here. First time. First time in a problem like this. Is the bottom, is that problem this. Note, look at the denominator is a quadratic, isn't it? Irreducible quadratic. This problem we're doing right now, the denominator is not quadratic, right? This is cubic. Now, one of the factors is irreducible, but the whole thing together is cubic. So you can't do what I was doing earlier, right? So how do we handle this? Well, for the linear factor, the x down there, we will put a over x. Okay, that's all beautiful. It's nothing's changed. That's the same as what we were doing before. Who can tell me what we do with the irreducible quadratic? Now it's so now it's the bx plus c over the irreducible quadratic, which is x squared plus 4. Okay, so when you see an irreducible quadratic in partial fractions, what goes on top is not just a number, but a linear expression, bx plus c. All right. Why do you think we will be happy if we work this out and get b and c? Why do you think we'll be happy to see this? Yeah, because we can do what we learned last class, right? I mean, I said last class, if we have a linear over irreducible quadratic by itself, then we can use either the way I like to do it or the way the book likes to do it, right? Two different paths there. So do y'all understand that this problem is going to become that problem? At least one portion of this problem will become that problem? Okay. All right, so let's go. How are we doing on time? We got a little bit of time. Okay, so here we are. Let's clear the fractions. I'm going to go a little faster here because of time. I'm going to just kind of hope that you could clear these fractions fast. So if I multiply both sides by the denominator, right, like x times x squared plus 4 here, and then same thing, x times x squared plus 4 here. Gone. We should get 2x squared minus x plus 4 equals, okay, here we're going to get a times x squared plus 4 because the x's cancel, plus, be real careful here, the x squared plus 4 cancel, we still have the bx plus c on top times the x. I'm going to expand out the right side because I want to use my calculator. Ax squared plus 4a plus bx squared plus cx. This gives me 2x squared minus x plus 4 equals the x squareds. I have an a and a b. Only have the cx and then the 4a. Anyone disagree? Everything look okay? I know I'm moving faster through this one. All right, let's match things up. A 2 in front of x squared. So a plus b has to be 2. -1 has to be c. And then 4a has to be 4. You following me? A plus b has to be that coefficient. The number in front of x has to match here, -1. And then the 4a, which is by itself, has to match the 4. You know what? This is too easy to do by the calculator. C I already know, right? This I know what a is, right? A is 1. And once I know what a is, if a is 1, right, this becomes 1 plus b is 2. So that means b is 1. No calculator necessary here. If you want to use a calculator, go ahead, but questions on how I got that? Sure. So 1, 1, 1, -1. 1, 1, negative 1 are my numbers. 1, 1, negative 1. So back to this. This becomes a 1. This is a 1, and this is a negative 1. So my integral now becomes integral 1 over x plus 1 in front of x, so x minus 1 over x squared plus 4 dx. The first one's easy, right? The first one's easy. Natural log x. The second one is a linear over an irreducible quadratic, right? Linear over irreducible quadratic, which is what we were knowing it would be. I don't want to say we were hoping for it, but that's what we got. So how do y'all want to do the second one? Do you want to split it in 2 integrals? That's fine with me. I will hesitantly comply. Here we go. I'm going to split it into 2. I'm going to pull the negative out of the second one. Is that all right? Okay. There we go. So splitting this up, x over this and then this over that. Pull the negative out. Why did you want to split it? Yeah, the middle one is a u sub, basic u sub. U is the bottom. Derivative is the top. You're off by a constant. And then the second one is arctan. Shit. The second one is arctan, right? I didn't even drink anything. All right. Let's do a u sub. Do I really need to do the u sub? I don't think I need to. I mean, you might need to on the side. That's fine, but I won't. What is it?
2x.
1 over 2. Natural log x squared plus 4. There we go. So from here to here is a basic u sub. Let u be the bottom, and you work that out on your own if you need to. And then over here, this one is 1/2 arctan of x over 2. That's formula 17, I believe. Formula 17. That was the very first thing we learned at the beginning of class last time. Remember this? Right there. That's what that last one is. So this one is formula number 17. And this one from here to here is a u sub, let u be the bottom. The derivative of that is 2x dx. You have to scale both sides by 1/2. And when you do that, the integral then becomes integral 1 over u du, but there was the 1/2 out front. Okay. There we go. All right. We're done. So a mistake that I see people make, all right? A mistake I see people make is this. They'll get an integral like this, okay? On a test. They'll get to this and they'll be like, oh, that's an irreducible quadratic on the bottom. What do I do for partial fractions? Oh, I do this. I do this. And then, Cruz, what do you do when you have an irreducible quadratic? What do you put on top? In this case, ax plus b, right? Over the irreducible quadratic. Do you understand what I'm doing here? What's wrong with this? The numerator already was a linear expression. So why are you going to try and figure out what linear expression would be on top when you know what linear expression is on top? Do you see what I'm saying? Like I already tell you, A is 1 and B is -1. So when you get to this point, that's where you have to do what we did last class. You do this part, you do this when you've got something like this problem where we start on our starting point our starting point is not irreducible quadratic. Our starting point is a cubic function. And then within it, you have to deal with it. But okay, I only have 5 minutes. Let's see. There was still more to do. Let me see. I think there was one more or two more. Yeah, I did that one. Did we do that one? No, I did my own. So we still have this one. Let me show you this one real quick. I really like this one. I'm not going to have the whole time to work it, but check this out. That looks pretty weird, right? First step would be what? Long division, right? But watch what I'm going to do here. Just check it out. Man, because they're so close to one another, aren't they? They're like almost the same thing. Now, you don't have to do the step I'm doing right now. Okay, you can do your long division, but I could rewrite this as 4x squared minus 4x plus 3 plus x minus 1 over 4x squared minus 4x plus 3. Isn't that the same thing? So like the bottom is this, right? And so what I did is I tried to rewrite the top to make it look like the bottom. So I put minus 4x plus 3. But to make it match the top, I had to add an x and subtract a 1. Do y'all see that if I added this x here and subtract the 1, I would have the top? But that allows me to split this right here. So do all of this over this, which would be what? 1 plus now what's remaining over the other part. So essentially, I just did the long division without actually having to do long division. If you do long division, this is what you'll get. Now, it doesn't always work that way. It's only because things looked really close to one another. So let me just, we got to end class here. Let me ask you, how would you handle that? What is it over what? Linear over quadratic. Your first question should be, is it factorable? If it's factorable, you're going to go partial fractions. If it's not factorable, then you're going to do what we did last class. So can you factor the bottom? Does it not factor? Oops. 12 and negative 4. What's that? The b squared minus 4ac. You could do that. Yep. So are we convinced it does not? Need two numbers to multiply to be 12, add up to be negative 4. Negative 6 and 2, but those won't add up to be, or those won't multiply to be positive 12. Right? So it's looking not factorable, isn't it? Which means don't go do partial fractions because it's irreducible, right? It's not factorable. So don't be telling me that this is going to turn into, ax plus b over this because you already have that, right? So this is where you'd have to use the technique from last class. Oh, by the way, this problem, you want to finish it off? If you want to finish that problem off, go and take a look at last class. And that is this problem, right? Wait, hold on. Not that problem. Hold on. It's that. See that? Remember when we did that? And I told you I do it like I like to do it, and then there's another way. That problem is the problem that we're working right now. So we've already done it. Okay, that's it. We are, yay. We can celebrate. Well, you still have to do the homework, but we can celebrate the fact that we are done with the techniques of integration. Now we move into applications. Areas under curves, areas between curves, volumes of solids of revolution, arc length, surface area, a lot of visual stuff, which is kind of cool. And then series will be right there around the corner waiting for us. All right, y'all have a great day. Let's stop the recording here. Question?